Hi learners, welcome again. Welcome to the program Data Mining. Our today's topic is Classification and Prediction, third part. So today I will be covering the topics Bayes classification methods, Bayes theorem, and naive Bayesian classification. Rule-based classification, in that I will be covering the rule extraction from a decision tree and the lazy learner, who are also the learning from our neighbors. Bayes classification methods. What are Bayesian classifiers? Bayesian classifiers are statistical classifiers. They can predict class membership probability, such as the probability that a given tuple belongs to a particular class. These are the classifier are going to check if the given tuple belongs to a particular class or not. Bayesian classification is based on the Bayes theorem. That is belongs to the Bayes theorem. Studies comparing classification algorithm have found a simple Bayesian classifier that is also called as a naive Bayesian classifier that to be comparable in performance with decision tree and selected neural network classifiers. So we have already completed our decision tree. Now in next part we will cover the neural network classifiers. So the naive Bayesian classifier is going to be compared with the decision tree and other type of neural network classifiers, right? Bayesian classifier have also exhibited high accuracy and speed when that is going to apply to the larger databases. Naive Bayesian classifier that assumes that the effect of an attribute value on a given class is independent of the values of the other attributes, right? So this assumption is called as a class conditional independence. Class conditional independence. So it is made to simplify the computation involved and in this sense is considered naive, right? So the word naive came from that because it is made to simplify the computations involved, so that it is called as a naive Bayes, right? So it is basically based on the Bayes theorem. So what is Bayes theorem? Bayes theorem is named after the Thomas Bayes, the person Thomas Bayes, a non-conformist English clergyman. He was the non-conformist English clergyman who did early work in the probability and decision theory during the 18th century. Let X be a data tuple. In Bayesian terms, X is considered evidence. Okay. As usual, it is described by measurements made on the set of n attributes. That is made on a set of n attributes. Let H be some hypothesis. What is hypothesis? That is none other than assumptions. Hypothesis is assumptions, right? So H, if let H be some hypothesis such as the data tuple X belongs to a specified class C. Okay. For classification type of problems, we want to determine P H upon X, the probability that the hypothesis H holds given the evidence, and we can call as observed data tuple X. In the other words, we are also looking for the probability that tuple X belong to class C, given that we know the attribute description of X. Understood? Now, how are these probability estimated? How are these probability estimated? We have to find out. So if PH, Px upon H and Px, PH, Px and The other term is Px upon h. These may be estimated from the given data, as we shall see next. Bayes theorem is useful in that it provides a way of calculating the posterior probability, that is none other than Ph upon x from Ph and Px. So the Bayes theorem will be the further that Ph upon x is equal to Ph upon x into Ph divided by Px. That is the posterior probability. Posterior probability. Right? So, if we are going to calculate the probability for the Bayes theorem, so we need to calculate these from this formula. Here, Ph upon x is the posterior probability, or we can say posteriori probability of h conditioned on y, on h considered as x. For example, suppose our world of data tuple is confined to customers described by the attribute age and income, respectively, that X is a 35-year-old customer with an income of $40,000. Suppose that X is the hypothesis that a customer will buy a computer. That is a hypothesis, that is an assumption that the 35-year-old customer will buy computer. That we had a assumption. So then Ph upon x. That reflects the probability that customer X will buy a computer, given that we know the customer's age and income. Right? So in contrast, Ph is the a priori probability of H. For example, this is the probability that any given customer will buy a computer, regardless of age or any type of other information for that matter. Right? So here we will only, regardless of age and income, the customer will only buy a computer. The posterior probability Ph upon x is based on more information, that is customer information, that the prior probability Ph, which is independent of x. So this was all about the Ph upon x term and Ph term. Similarly, Px upon h is the posterior probability of x conditioned on h. So that is, it is the probability that a customer X is 35-year-old and also earns the $40,000, given that we know the customer will go buy the computer, right? So this is the condition. The customer is 35-year-old and also earning $40,000, and he will buy the computer. So here the term Px is the prior probability of X. Using the same example, that is, we can see here table. From the table, it is the probability that a person from our set of customers is a 35-year-old and earns $40,000. So here we are having the column age, income, student, customer rating, and boys computer, and different type of class labels as a record. For example, predicting a class label using Bayesian classification, we wish to predict the class label of a tuple using Bayesian classification. Given that the same training data as in the example for decision tree induction, the same example we have also taken for the decision tree induction. So the training data were shown earlier in the above table, in the earlier slide, and the data table are described by the attribute age, income, student, credit rating. These were their attributes, their columns. So the class level attribute buys computer has two distinct value. that is yes or no. Let C1 correspond to the class by computer is equal to S. By computer is equal to S, and C2 correspond to the by computer is equal to no. By computer is equal to no. Okay. So the tuple we wish to classify is X is equal to in bracket age is equal to youth, income is equal to middle, student is equal to yes, and credit rating is equal to fair. This is some rule. So we need to examine, we need to maximize Px upon Ci dot Pci for I is equal to 1 and 2. So PCI, the prior probability of each class, can be computed based on the training tuples. So here we will calculate the P for Bayes computer is equal to S. So that will be the 9 upon 14. 9 upon 14. So how we'll get? We'll get from the same formula, which is the Px upon Ci dot Pci. So we'll get the P, we'll get same from the same 9, and we'll get the 14 from the Pci. So if we'll divide by 14, it will come as a 0.643. For the other condition, when Bayes computer is equal to no, so the condition, the numeric values will find out as a 5 upon 14. So the value will come as a 0.357. To compute Px upon Ci for I is equal to 1 and also 2, we compute the following conditional probabilities. So the some rules are P of age is equal to youth when the age is equal to youth and the Bayes computer is equal to also yes, so that the formula, from the formula we'll get the value is equal to 2 upon 9. So 2 upon 9 is equal to, that value will come as a 0.222. When P of age is equal to youth and by computer is equal to no, the value will come as a 3 upon 5 is equal to 0.6000. Also, if the condition is P of income is equal to middle and by computer is equal to yes, the value will come as a 4 upon 9, that is 0.444. If the income is equal to medium and by computer is equal to no, the value will come as a 2 by 5. So the final value will come as a 0.400. If the student is equal to S from the table and by computer is equal to S, then the value we'll get is 6 upon 9, that is nothing as 0.667. So if we have say Q count to which we add 1, then we must remember to add Q to the corresponding denominator using the probability calculation. Okay. Here again we'll find out the rules, that is P student is equal to S and by computer is equal to no. So the value will come as a 1 upon 5, that is 0.0200. If the credit rating is equal to fair and by computer is equal to S, the value will get as a 6 upon 9, that is 0.667. If the credit rating is equal to fair and by computer is equal to no, the value will get as a 2 upon 5, that is 0.400. So using these type of probability, we obtain, what will obtain? The P of X by computer is equal to S is equal to P is equal to youth by computer is equal to yes into P whole of the into P income is equal to middle and by computer is equal to S into P student is equal to S mod of by computer is equal to S into P of credit rating is equal to fair mod of by computer is equal to S. So the value we have already calculated earlier, that is 0.222, 0.444, 0.667, 0.667, and the result will be the 0.044 for that. Similarly, if the by computer is equal to no, so we'll calculate the for the same. If that was for S, we'll calculate for no. So the calculation we have already done, so we'll include that 0.600 into 0.400 into 0.200 into 0.400. That is, the result is 0.019. So to find the class Ci that maximizes P of x upon Ci into P of Ci, we compute the P of x computer is equal to S into P of by computer is equal to S. That is 0.044 into 0.643 is equal to, the result will be the 0.028. Again, we'll calculate for the when the by computer is equal to no into when the by computer is equal to no, from the both of the rules. That is from the second, and earlier we have also calculated from the directly from the table. So we'll calculate that. The value will be the 0.019 into 0.357. The result will come as a 0.007. So therefore, the naive classifier predicts Bayes computer is equal to yes for the tuple x. So that was the calculation for the naive Bayes classifier. So from there we have to calculate, we have to find out the likelihood probability for the same. So there are many applications of naive Bayesian algorithm. These are real-time prediction. Naive Bayes is an eager learning classifier also, and it is surely fast. So thus it could be used for marketing predictions in real-time applications. The other example is multi-class prediction. So this algorithm is also well known for the multi-class prediction feature. Here we can predict the probability of multiple classes of target variable, right? So the text classification of spam filtering, or we can also call as a sentiment analysis. So the text classification is nothing but we can use as a spam filtering and sentiment analysis. So the naive classifiers mostly used in the text classifications due to the better result in the multi-class problems and independence rule. That has a higher success rate as compared to any other type of algorithms. These are more applications for the spam filtering, that is also identify spam email filtering and sentimental analysis. In social media analysis, we are using that to identify positive and negative type of customer sentiments. So there are other type of application, that is recommendation system, naive classifiers and collaborative filtering together builds an recommendation system. That uses the machine learning and data mining techniques to filter the unseen information and predict whether a user would like a given resource or not. So, for example, the best recommendation system is the Amazon, we can say the Flipkart. So if we have added some of the item in that, so in the future it is going to predict for the what you have to purchase similar to the product. So that will recommend to you on the basis of naive Bayes classifier and collaborative filtering. Another example is credit scoring, medical data classifications, and real-time predictions. In real-time prediction, we can also use naive Bayes algorithm because of the use of machine learning and data mining techniques. Another method is rule-based classification for classification. So in this section, we look at rule-based classifiers, where the learned model is represented as a set of if and then rules. So here that if we can see as a rule-based classification. So here some of the rules will be there that on the basis of that we are going to going to classify the classifier. Okay, so here we will introduce the if then rules. So we first examine how such rules are used for classification. We then will study way in which they can be generated, either from a decision tree or directly from the training data using a sequential covering algorithm. So first is using if-then rules for classification. The rules are a good way to representing information or bits of knowledge, right? So a rule-based classifier uses a set of if and then rules for classification. An if-then rule is an expression of the form if condition and the then conclusion. If, then we will write the condition, and then here conclusion. So like this it will work. For the example, rule R1 is equal to if age is equal to youth and student is equal to yes, then it is going to buy a computer for S. Okay, this was the rule. The if part of the left side of a rule is known as the rule antecedent. That is nothing but a rule antecedent. We can also call it as a precondition. The then part, or right hand side part, is the rule consequent. That is rule consequent. Right? So in the rule antecedent, the condition consists of one or more attribute tests, that is age is equal to youth and student is equal to yes, that are logically ANDed. Then it will end it with the logic AND. The rules consequent contains a class prediction. In this case, we are predicting whether a customer will buy a computer in the first R1 rule. R1 can also be written as a same of the rules this we have seen in the earlier slide. We can write it as a R1 is equal to age, in that age is equal to youth, ascends student is equal to S. That is depend on the boy's computer is equal to S. Okay, so if the condition, that is the if the attribute sets in a rule antecedent holds true for a given couple, we say that the rule antecedent is satisfied, or simply that rule is satisfied, and that the rule covers the tuple. So that was in the condition. A rule R can be accessed by its coverage and accuracy. We can access also the rule by its accuracy. So given a tuple X from a class labeled data set D, let N covers be the number of tuples covered by R. N correct be the number of tuples correctly classified by R, and the D be the number of tuples in D. So we can define the coverage and accuracy of R as a coverage of R is equal to N covers divided by D, and the accuracy of R is equal to N correct divided by N covers. N correct divided by N covers. So that is a rules. That is the rules coverage is the percentage of tuples that are covered by the rule, that is their attribute values hold true for the rules antecedent. For a rules accuracy, we look at the tuple that it covers and see what percentage of them the rule are correctly classified. So that was all about the coverage and accuracy. For example, rule accuracy and coverage, let's go back to our data in earlier table, the all electronics table. There are class level tuples from all electronic customer database. Our task is to predict whether a customer will buy a computer. So consider the rule R1, which covers 2 of the 14 tuple. There are 14 tuples, so it will take 2 tuples. It can correctly classify both of the tuples. Therefore, the coverage of R1 is equal to 2 upon 14 from the formula, that is 14.28%. And the accuracy, if we calculate the accuracy of R1 rule, so that will be the 2 upon 2, that is 100%. So let's see how we can use rule-based classification to predict the class level of a given tuple X. If a rule is satisfied by X, the rule is said to be triggered. So if the condition will be satisfied, the rule is said to be triggered. For example, suppose we have the rule X is equal to, where age is equal to youth, comma, income is equal to medium, comma, student is equal to S, and credit rating is equal to fair. That is a rule. We would like to classify the X according to the by computer. The X satisfy R1, which triggers the rule. So here the X is already satisfying the rule R1. That is nothing but triggering the rule. So if the R1 is the only rule satisfied, then the rule fires by returning the class prediction of X. Okay. So here triggering does not always mean firing, because there may be more than one rule that is satisfied, right? So if more than one rule is triggered, we have a potential problem sometimes. What if they each specify a different class? That is also can occur. So if in the some other cases, what if no rule is satisfied by X? So what we will do in this type of condition? So we'll tackle the first question. If more than one rule is triggered, so we need to conflict resolution strategy to figure out which rule gets to fire and assign to its class prediction to X. There are many possible strategies. We will see. We look at two, namely size ordering and rule ordering. The size ordering scheme assigns the highest priority to the triggering rule that has the toughest requirement, where toughness is measured by the rule incident size. That is the triggering rule which the most attribute test is fired. So that was the size ordering scheme. In the rule ordering scheme, that prioritize the rules beforehand. The ordering may be class ordered, we can say rule based. With the class based ordering, the classes are sorted in order to decreasing importance, such as by the decreasing order of prevalence. That is, all the rules for the most frequent class come first. Then the next prevalent class come next, and then so on. So like this, we will obtain the size ordering scheme and rule ordering scheme on that. With the rule-based ordering, the rules are organized into a one long priority list. That will be organized into the long priority list according to the some measure of the rule quality, such as accuracy, coverage, or size. Size is nothing but number of attribute tests in the rule antecedent are based on the advice from the domain experts also. So when the rule ordering is used, the rule set is known as a decision set. That is, will be known as a decision set. With rule ordering, the triggering rule that appears earliest in the list has the high priority, and so it gets to fire to the class prediction. So any other rule that satisfy X will be ignored after that. So most of the rule-based classification system uses a class-based rule ordering strategy. So if we can say in the first strategy, overall the rules are unordered. They can be applied in any order when classifying a tuple. So that is a disjunction logical OR that is employed between each of the rules. So each of the rules that represents a standalone nugget, a piece of knowledge. right? So this is in the contrast to the rule ordering decision list scheme, for which rule must be applied in the prescribed order so as to avoid some type of conflicts. So each rule in a decision list implies the negation of the rules that come before it in the list. Hence, the rules in a decision list are more difficult to interpret also. That is more difficult to interpret also. So now that we have seen how can handle conflict, right? So let's go back to the scenario where there is no rule satisfied by X. So there will be a question, how then can we determine the class level of X? Let's see. In this case, a fallback or default rule can be set up to specify a default class based on the training set. So this may be the class in majority or the majority class of the tuples that were not covered by the any rule. So the default rule is evaluated at the end. If and only no other rule covers X, the condition in the default rule will be the empty. In this way, the rules fires when no other rule is satisfied, right? In the following sections, we examine how to build a rule-based classifier. So the second the second method is rule extraction from a decision tree. We have learned how to build a decision tree classifier from a set of training data in the earlier course. Here, decision tree classifiers are a popular method of classification. It is easy to understand how decision tree work and they are known for their accuracy, right? So the decision tree is widely used for the classification. The decision tree can become a large and difficult to interpret sometimes. In this subsection, we look at the how to build a rule-based classifier by extracting if and then rules from a decision tree. If you are having a decision tree, then how we are going to build a rule-based classifier for that? So in comparison to the decision tree, then if and then rule may be easier for the understanding for the humans, particularly if the decision tree is very, very large. So then we will use the rule extraction from a decision tree. So to extract rule from a decision tree, one rule is created for each path from the root to a leaf. From the every leaf, we are going to make some rule for, that is going towards the root. Yes. So there will be some set of rules for that. So each splitting criteria along a given path is logically ANDed. So that will be ANDed with the AND to form the rule antecedent, that is if part, right? In the then part, the leaf node holds the class prediction, that is forming the rule consequent, that is then part. So a disjunction, logical or implied, between each of the extracted rules, okay, or will be applied. Because the rules are extracted directly from the tree, they are mutually exclusive and exhaustive. What is mutually exclusive? That means that we can't rule conflicts here, that the rules cannot conflict here, because that no two rules will be triggered for the same tuple. So that is the mutually exclusive. It means that we cannot have rule conflict here because the two of the rules will not be triggered for the same of the tuple, right? We have one tuple, one rule per leaf, and any tuple can map to the only one of the leaf. That was the mutually exclusive. The mutually exhaustive means that there is a one rule for each possible attribute value combination, so that this set of rules does not require a default rule. Therefore, the order of the rules does not matter. They are unordered. Basically, they are unordered. So this is the decision tree we have seen in the previous course. The final decision tree, which is having the condition in that the age of the student and the credit rating for the youth, middle-aged and senior is classified with the S and no. For example, here we are going to extract classification rules from the decision tree. Then the decision tree of the above figure can be converted to the classification if then rules by tracing the path from the root node to each of the leaf node in the tree. So the rules extracted from the figure as follows. The first rule will we will take as a R1, that is, if age is equal to youth and the student is equal to no, then everybody is going nobody is going to buy a computer, that is no. The second rule is if age is equal to youth and student is equal to yes, then they are going to buy a computer. The third rule is if age is equal to middle age, and then they will buy a computer. If in the fourth rule, if age is equal to senior and credit scoring is excellent, then they will buy a computer. If in the fifth rule, if the age is equal to senior and credit rating is equal to fair, then nobody is going to buy a computer. So that is very easy to extract from the decision tree, and that is feasible also. Since we end up with one rule per leaf, the set of extracted rules is not much simpler than the corresponding decision tree. Because we have to write some of the rules in, there can be a language problem also, there can be mistake. So the graphs are always better, we can say, from this line. So the extracted rules may be even more difficult to interpret than the original tree in some of the cases, right? So larger decision tree suffer from the subtree repetition and replication also, right? So the resulting set of rules extracted can be large and difficult to follow, because some of the attribute test may be irrelevant or redundant because of the larger data set. So the plot that will be thickened. Although it is easy to extract rules from the decision tree, we may need to do some more work by pruning and resulting the rule set. Because we have got the set of rules, 5 rules, right? Although from that we have to write all the 5 rules every time. So we can also prune or remove some type of rules, and we will get a few rules for the result. That is always better. So how can we prune the rule set? For that, for a given rule antecedent, any condition that does not improve the estimated accuracy of the rule can be pruned. That is the condition that is removed, thereby generating a rule, right? Here, C4.5 extract rule from an unpruned tree and then prunes the results using a pessimistic approach similar to its tree pruning method that we have seen in the earlier course. The training tuples and their associated class levels are used to estimate rule accuracy. So, however, because this would result in an optimistic estimate, alternatively, the estimate is adjusted to compensate for the bias, resulting in a pessimistic estimate. In the addition, any rule that does not contribute to the overall accuracy of the entire rule set can also be removed. Other problems also arise during the rule pruning. However, as the rules will no longer be mutually exclusive as well as exhaustive. For conflict resolution, C4.5 adopts a class-based ordering system. So in that case, we have to use the class-based ordering scheme. It groups together all the rules for a single class and then determines ranking of these class rule sets. Within a rule set, the rules are not ordered. C4.5 that orders the class rule sets so as to minimize the number of false positive error. False positive. So what is false positive? If where a rule predicts a class C but the actual class is not C, that is a true false positive. right? So the class rule set with the least number of false positive is examined first. First we will examine the which is having the least number of false positives. So once the removing of the rules is completed, a final check is remove any duplicate. If we will have the redundancy, then we will going to remove that also. So when choosing a default class, C4.5 does not choose the majority class because this class will likely have many rules for its tuples. Instead, it selects the class that contains the most training tuples that were not covered by the any of the rules. Lazy learners. This is also the classification, right? So eager learners, when given a set of training tuples, will construct a generalization, that is classification model, before receiving new tuples to classify. So the classification methods: decision tree induction, Bayesian classification, rule-based classification, classification by propagation, support vector machines, and classifications based on association rule mining. That all are example of eager learners. So what is lazy learners? Although we can think of the learned model as being ready and eager to classify previously unseen tuples. Imagine a contrasting lazy approach in which the learner instead waits until the last minute before doing any model constructor to classify a given test tuple. Imagine a contrasting lazy approach in which the learner instead waits until the last minute before doing any model construction to classify a given test tuple. That is when given a training tuple, a lazy learner stores it, or does only a little minor processing, and also waits until it is given a test tuple. So that is lazy learner approach. That is only when it sees the test tuple does it perform generalization to classify the tuple based on it similarly to the stored training tuples. Unlike eager learning methods, lazy learners don't do less work when a training tuple is presented and more work when making a classification of numeric type of predictions, right? So because the lazy learners store the training tuple, or we can say instances, they are also referred to as the instance-based learners. Even though all the learning is essentially based on the instances, based on the chances. We look at one example of lazy learners in the earlier slides, K nearest neighbor classifiers. So that was all about some of the methods of classification. We have covered the module 3 here. We will meet in the next module. Thank you for watching.
Like, share and subscribe. Hit the bell icon for more updates.